Now, this slide is obviously very busy. There's a lot of components um, that go into play with fuel control. And, clearly there's a lot of different components we have to look at. So the best approach, in my mind, is to break it down into chunks. And so the stages is what I use to describe it. So first of all, the first stage I want to look at is the calculation stage. This is where the basic pulse width of the fuel injector gets calculated. Now, the first thing we've got to do is we've got to determine, are we dealing with a speed density car, which uses a MAP sensor, or a mass airflow car that uses a mass airflow sensor, because we're going to have to think differently about each of those systems. The next stage is the delivery stage. This includes fuel from the fuel pump all the way to the tip of the fuel injector. So this is a different stage. This is the next stage of delivery. Once the calculation made, the fuel has to be delivered to the cylinder. And the final stage, of course, is feedback. And I've got two different sensors pictured here. The top one is an oxygen sensor, and the bottom one is an air fuel sensor. The air fuel sensor kind of throws us a curve when we're looking at fuel trim, because the data we see on our scan tools is going to be significantly different when we're dealing with an air fuel sensor. So the first system is speed density, and remember that a calculation for fuel is made by weight. So what the speed density system does is create a very effective guess as to the weight of the incoming air, and so the PCM can calculate the weight of the fuel that needs to go with it. So by using a pressure sensor and RPM, the speed density system can pretty clearly figure out how much air is going into the engine by having a design table inside the PCM that tells it that at a specific RPM and a specific pressure, this amount of air should be entering the engine. Now, for each of these sections that I broke out, I'm going to do three things. I'm going to give just quickly talk about the way it works, and then we're going to take a look at the effect of a failure on fuel trim, and then we're going to look at how we might eliminate this as a cause. So the way that we just covered how this worked. Next, we're going to talk about the effect of a failure. If the MAP sensor is unresponsive, fuel trim could be lean off idle. So what I'm talking about is a MAP sensor that doesn't change when you open the throttle. That's fairly easy to check by looking at scan data. What's hard to check is to see if a MAP is out of calibration. If a MAP is out of calibration, a fuel trim could be lean under all conditions. So it's really the best place to test a MAP sensor is key on, engine off. And it needs to be comparable to the baro that you have seen on good running cars at your location. The weather station baro is not how you want to compare a MAP, because the weather station baro is corrected for elevation. And so at my house at 3,000 feet, a car would show me a baro of 27 inches, but the weather station on a sunny day would say I had 30 inches of barometric pressure. It's a different thing. So you want to look at some good cars, see what the baro reading is, and that becomes your number. Vacuum leaks affect a speed density car differently than they do a mass airflow car. So you want to keep that in mind, that a vacuum leak would probably just increase the engine speed at idle, may show up more under the idle control solenoid PID than it will under the fuel trim PID. And finally, to eliminate this MAP sensor as your cause, you do want to check it key on, engine off, and snap the throttle and verify that it responds. Now, our big player here in calculation is mass airflow. It's the most common sensor to have a problem with. You know, the mass airflow is supposed to directly measure the air mass by measuring current flow that is required to keep a wire hot inside of it. The theory is the more air flows across the wire, the more current is needed. The throttle position sensor in a mass airflow car is just a transitional sensor. It says, hey, the throttle is increasing or decreasing or idle or wide open. The other thing I want to mention is that the coolant temperature, a lot of people think it has a big effect on newer cars when it's at operating temperature, but that is certainly not the case. As soon as the PCM has seen that the engine's gone through a warm-up cycle, it pretty well ignores the coolant temperature sensor. Another thing about the mass airflow sensor is that it really doesn't measure all the air coming into the engine. It actually measures a sample of the air. that sample can get a skewed reading by some debris which happens to be lodged on the air filter or on the screen in front of the sensor and disrupts the airflow. Another item that can disrupt the airflow into the sensor is a malformed air filter that has a cone that's the wrong size. So again, if the mass airflow sensor is out of range or dirty, you basically end up with a lean DTCs. Remember, on this system, a vacuum leak is lean all the time, always going to be lean. A duct air leak could be lean at idle and under load. So how do you eliminate the mass airflow sensor? Well, the snap test has been around for a while. We may also want to look at the engine load pit under load. We also might want to look at fuel trim both at idle and compare it to being under load. And then there's a wide open throttle calculation that you can use. If you test drive the vehicle wide open at 5,000 RPM, if you take the displacement of the engine in liters, multiply it by 40, that should be approximately what the output of the mass airflow sensor is at 5,000 RPM. So there's a couple of ways that you can eliminate a mass airflow sensor as being your problem. The delivery, of course, is the fuel being supplied to the tip of the injector. In my mind, there's two parts to delivery. It starts at the fuel pump, goes through the filter. You guys have fixed these kinds of problems for many years. And the good news is that it's pretty easy to eliminate because you check your fuel trim at high RPM versus idle. And drive the vehicle wide open throttle and watch the O2s. They should be able to stay rich. And if they don't, you probably have a fuel delivery issue. Also, we want to consider, when we think about the fuel injectors, we have to consider the effect of deposits both on the tip of the injector and deposits on the intake valve. And these deposits can cause a dilution type of a lean condition. The good news is it's going to almost always happen at idle. And to eliminate this one, you bring the engine off idle and watch your fuel trim. If the fuel trim gets a lot better as soon as you bring it off idle, you're clearly dealing with a dilution issue. Now, of course, the feedback system uses your fuel trim, and the short-term fuel trim is something that cycles basically as much as the O2 sensor. The whole goal is to put the right mixture into the catalyst for low emissions. But what I wanted to say about the short-term fuel trim is that you really can't consider it in a static moment of time. You have to consider it over time. That's when a graphing scan tool really comes into play. So if you've got a scan tool that can graph the O2 sensors and the fuel trims, you're ahead of the game because you can test drive the car and look at trends while you change the operating conditions. So another thing that will happen with an O2 sensor is the heater goes bad. And that's a pretty quick test because you run the engine at 2,000 RPM until the oxygen sensor gets hot and it's responding well. And if it responds well by heating it, and then it starts to slow down when you go to idle, you know, that's a pretty good clue that you got a heater issue. The long-term fuel trim is driven by the short-term, obviously, and it's a very good tool for us to look at when we're thinking about a lean DTC. We want to see what the long-term fuel trim has stored as when we get, in different operating conditions, and we can use that to determine what is going on with the fuel trim on the vehicle.